I'm a little bit more of a science person. Bas, how would you describe yourself?
I'm more of an engineering person.
And what we typically do is our employer gets us these Fridays, and we're allowed to do whatever we want. Like once a month, do whatever. And our favorite hobby is to over-engineer a funny problem. So, Bas, oh, sure. Yeah, but we'll do that when they. So I see that the laptop has now been moved upstairs, so that should be fine.
So these should be live. That's over.
Ah, okay, grand. Well, we'll now do the thing where we sort of stand in the middle here. But what I'm about to tell you is a story about an algorithm, and there's a very cool and highly applicable part of the algorithm, and there's a not so applicable part about the algorithm. But there's something very general that we discovered that we're actually pretty damn proud of. What I will say, though, is I wouldn't approach it the way that we did. Grand. Okay, so there's a button at the top. Yes. Yeah, okay. Yeah. Play. All the way at the top. Nope. Nope. Left. Again, this is what is messing up the timing. So, what we'll do is when I do... Yay! So, Bas, if we wave, that's when we want the next slide, right?
Yeah,
Let's do that. Okay, so let's see if this works. You can press spacebar. Hey! Okay. Welcome everyone. We had a slight technical error, but we'll make it work. What we'll be talking about today is a silly problem that we're going to over-engineer. And when I say over-engineer, I mean over-engineer in all caps. This is a card game that I usually love playing. However, that's my lovely girlfriend, and my lovely girlfriend typically wins. Very typically, she wins. She actually wins quite often. And this got me thinking. I bought this book called Real World Algorithms, and as my girlfriend was sort of counting how many points she got and I didn't, I figured out, let's maybe use an algorithm here. Can I use an algorithm to get better at this card game? So the goal is, we're going to find a helpful algorithm. This seems like an easy problem. Surely we can solve with an algorithm. If need be, I'll borrow my boss's credit card for any cloud resources I might need. I'll learn from it, and then I'll probably win from my girlfriend once in a while. That'd be nice. This game of Sushi Go, though, it can get quite deep. And the small thing, like, we have to keep it simple. I want to get better at the card game myself without the aid of a laptop. My girlfriend would really think it's cheating if at every decision I need to make, I need to consult the terminal. I think that's fair, right? So none of that voodoo, reinforcement, deep learning kerfuffle. I'm not going to do any of that. So also another reason to keep it simple, I know who I am. I'm going to over-engineer it anyway. I'll find help with the over-engineering. So we really want to try and keep it simple because we're going to make it over-engineer anyway. So again, this is the card game, and just the gist of it, what the computer science problem is. These are the cards that you can play, and I just want to figure out which cards are better than others. So I have a list of all the card names. And the only thing I want that list to be in the right order. The best card should be in one end, the worst card should be in the other end, and everything needs to be ordered correctly. And if you want to do that, you need a way to simulate an order. So I've got this function, the code's not too important, but you can put an order of cards in there, and I can simulate a bunch of times against a random player, and that'll be my score function. So I want to optimize the order. This is how I'm going to optimize. This is what says if an order is better or worse. Unfortunately, I've got 14 cards, so that's quite a lot of combinations. And if you think about it, this is very similar to the traveling salesman problem. The traveling salesman problem is also ordering cities in which you're going to visit. So I already knew this, like winning from my girlfriend was going to be hard, but this implies that winning a card game is NP hard. So, okay. You can smell the over-engineering from a distance at this stage. However, and this is sort of a thing that I want to give you before you go home, we now know it's an NP-hard problem, but it doesn't mean that we should stop thinking. Sure, we've got lots and lots of combinations here, but maybe we can think and make the problem already a bit easier. And the thing is, yes, these are the cards, but I play this game well enough that I do know that some cards are inherently worth less than other cards. You can read that from the rule book. You don't have to, like if you don't know anything, you might not know this, but just from reading the rule book, I do know that if there's ever an order in which an egg is worth more than a squid, that order is already wrong, so I shouldn't even consider that. Now, if you take this into account, then already the number of combinations decreases by quite a bit. It's at a 36 speed up if you look at it that way. And that is one lesson at least. We still have quite a few combinations left, but this small little thought, this small little, hey, before I do any sort of code, can I, oops. The hardware is being patched at the moment. But if I have any form of thought that I can put in before I do any code, this is a 36 speed up. This saves me 36 the amount of processing power. Never forget to think before you code. More people should do this. So even with this reduction, it's kind of a lot of compute I probably got to do still. It's not a small search space. And what makes it worse, it's not that I only have to search there, but I got to simulate a whole lot. For every one of those combinations, if I'm going to do brute force, I need to simulate at least 5,000 times to get a reasonably accurate score metric. So, okay, how about I'm just going to do a 101 on evolutionary heuristics. I'm not going to brute force it, but what I'm going to do is I'm going to say, here's a couple of orders. I've simulated them. I've got scores. What I'll do is I'll throw away the bad ones, keep the good ones. And what I'll do is I'll try to take the ones that are good and make more orders that are like it, but a little bit different. If I repeat this a whole bunch of times, you might recognize this as sort of the genetic way of doing it. You will come to a cool conclusion that the green parts, the stuff that's heavy, that's where all the simulation happens, that's embarrassingly parallel. So that bit, we can do some scaling. Yeah, and then it helps if you've got an engineer. So we found a solution, and Bas will tell you a bit more about it. It's a bit unconventional. It's marketed for a totally different purpose. But we actually got something to work here, and Bas will tell you a little bit more about that.
Okay. Yeah, next slide. All right, so how to get this working in a nice way. Vincent showed with some simple mathematical tricks, you can get the search space down from 87-something billion down to 2 billion possible combinations. But it's still quite a lot of combinations. If you were going to brute force all the possible combinations to find the best order to win your card game, let's say a single simulation takes 0.1 second. You're still going to be waiting for over 7 years. So it's not very optimal. And we needed a bit better way to do all these simulations. So there's a lot of ways to approach this problem. Before this whole little project, we haven't worked with lambdas before, and we thought, hey, we need a lot of CPU power for this, and Amazon has this service called Lambda nowadays. So let's try to use it for this use case. So it's a compute service that lets you run code without provisioning or managing servers. What it means, you upload your code or your function to Amazon, and Amazon will deal with all the managing and scaling and provisioning of this service. So it doesn't matter if you have one request going there every now and then, or 1 million requests. Amazon will do all the scaling of your Lambda function. So it's a bit like this. You have your Lambda function. At some point, you're going to make a request, and the request is going to return to you. Next moment, you want to run a lot of simulations. And the nice thing about Lambdas is it scales almost instantly. So straight away, you have access over 1,000 Lambdas. There's a lot of ways to trigger it. So with a Lambda, you upload your function into a Lambda function, but you need a way to call this Lambda function. So Amazon provides you a couple of ways to do so. So SNS, SQs. You can also call it over HTTP, and Amazon has another service for this called the API Gateway. So you have your... Yeah, so let's say this is Vincent. He makes an API call to the API Gateway. We have an endpoint there called simulate, and this will make the call to your Lambda function. It will run your simulation and then return your result. The API Gateway is basically like an endpoint where you can add like a REST API. So besides simulate, you can just add your own functionality behind it. And API Gateway will do many management things for you. So let's say your endpoint somehow leaks to the internet and you get DDoSed. the API gateway will manage this for you and do some throttling on all the traffic. Anybody who's ever worked with Amazon before knows how you have to go clicking around in the UI, or if you want to set it up automated, yeah, you have to learn some CloudFormation or some other deployment tool, which might take a bit of time, which you might not want to do if you have this cool problem you want to work on. So there is a tool for that. It's called Chalice. Chalice is a CLI tool to create applications using Lambdas and gateways, and it can also do some other things. What this allows you to do. So let's start with a Hello World example. First, you run pip install Chalice. You will get access to the Chalice command line tool. Let's create a Hello World application with Chalice new project Hello World. What this does is it creates a Hello World directory for you with some, basically a skeleton project for you. So there's a Hello World directory with an app.py in there. This app.py contains your API. There's a git ignore and requirements file. And there's a .chalice directory. This contains the metadata of your Lambda function. So once you deploy your Lambda function with Chalice, it will store the metadata of your function in there, and which is nice because you can check this into Git and then share the same Lambda function with your colleagues. So when you run Chalice deploy, a couple of things happen. It will package the directory into a zip and will upload it to Amazon. So that's a deployment package. It will do some stuff like creating IAM policies and rules for you. It will register a Lambda function at the Amazon side, create a REST API, which is this API gateway, and then we'll deploy the whole thing. The last line, you see this REST API URL, and this is the public endpoint which you can use to call your Lambda function. This is what the app.py looks like. So it has a bit of the feeling of a Flask app. Most important part is the app.route decorator. So this route is like a magic thing in Chalice. It creates a API gateway endpoint for you, in this case on the root, and it will map every call to that endpoint to this function which you have below it. It allows you to define multiple routes, and you can very easily create a nice little API endpoint in the cloud. And it's nice because you can basically deploy this thing with just running on the command line, and you don't need to worry about managing servers or whatsoever, and it scales automatically. One last tool to introduce. So on the client side, we have Lambdas and API gateways with Chalice. On the local side, we wanted to use a tool called Fire. Fire is a tool to create very simple command line interfaces. So let's say you have a script with some functions, and you want to convert this into a command line tool. With Fire, it's super easy. So you have your main if name equals main. In there, you define basically your mapping between the commands from your command line tool to functions in your script. So in this case, we have two commands, hi and simulate, and they map to hello and simulate. And the arguments for these functions automatically get mapped into flags in your command line tool. So with just a click of a button, we now have a command line tool which can run simulation. Let's say in this case, we give it 10 workers. And then, well, let's scale this up a little bit. And now we have, just by changing the number of simulations to 900, we have 900 calls to our Lambda functions. So very cool. So let's let's try to abuse these Lambdas. So for Iron Range, many simulations. Let's go and simulate. It's not very feasible because what it's going to do is going to call your Lambda function. We'll wait until the simulation is done and get back to you. And we'll do this back and forth over 2 billion times. So obviously that's going to take a very long time. And you don't want to be waiting that long. So there's a couple of ways to do multiple jobs simultaneously. You can do some multi-threading stuff. But today we're going to look into async I/O. So we run on a single thread, but we're going to want to run tasks concurrently. Just to set the context, here's a synchronous example. We have a long task. Let's say this is our simulation, in which we, in this case, sleep. We call this 5 times, and then at the end we're going to print how long this takes. Well, very straightforward. So what happens is we do a call to our sleep function. It's going to sleep and then print process task 0. This goes back and forth 5 times, and in the end we see completed in 5 and a little bit seconds. Now, asynchronous example with async I/O. So there's a couple new magic keywords you get with async I/O. But the biggest thing you need to do is on line 12, you have to instantiate this event loop. So this runs on a single thread, and this is basically like a scheduler. You add tasks to this event loop, and the task will tell, with the async and await keywords, they will indicate to this event loop when the event loop can go and run other tasks. So let's say you have this sleep function, and with the await keyword, you can tell the event loop, hey, I'm now going to sleep, but in the meantime, you can go and do other stuff. So in this example, what will happen, it will start these 5, it will call this long task for 5 times, but they're all going to say, hey, I just started, but in the meantime, this event loop can go process other stuff. At some point in time, my main process of execution will return to me. And the nice thing about it is that you can basically trigger these asynchronous tasks at the same time, and then they will return to you almost at the same time. So you see they complete in about a second. And there's one thing to note with asynchronous programming. You don't know when task will return to you. So yeah, let's say you make an HTTP call. It could take 1 second, it could take 3 seconds. And you have to account for this in your program. That task, the order of task is not guaranteed, of course. So you make a call, and at some point in time, you will return your result. The last thing, if you're going to make HTTP requests with async I/O, you have to use this AIO HTTP library, in which you have this session context. On line 12, you have to open this AIO HTTP client session. So you have a single session, and from that client session, you run all your asynchronous tasks. So in our case, we thought, we want to really brute force all these simulations, and we want to, let's just start 1 million concurrent coroutines. I think I forgot to introduce the coroutine concept. So if you prefix your function definition with async, it will tell async I/O this can run in a separate part outside the main process, and this thing is called a coroutine. So if you run many asynchronous tasks, you will run many coroutines, and they will open a file on your file system. And a file system has a limit to the number of open files. So if you really open up too many coroutines, yeah, your machine will not be able to handle them all. So you have to use some tricks for that. One included in the async I/O library is called a semaphore. I had some notes here. Anyway, so semaphore is basically a limit to the number of coroutines you can have open. What happens if you call a new coroutine? A semaphore is basically a counter, and once a new coroutine opens or tries to open, it will check with this counter, hey, is there still space for me to open a new coroutine on the system? If the counter has reached its maximum, it will basically just block until other coroutines have finished their execution, and once that has happened, then you can start new coroutines. So I introduced a couple of tools, a couple of libraries to do some asynchronous processing. Let's see what we can do with it.
So at this stage, I'm the evil scientist who just got a whole bunch of resources. So, yay. The idea is, before we're going to do anything serious, we're still sort of over-engineering, so let's benchmark some things. I'm going to do a deployment of Lambda. We're just going to start out clean. The idea is, let's just boom, send 1,000 things there. Let's just make them sleep so we can sort of really measure the overhead and check how long it takes before everything goes back. And two situations are what you're seeing here. On the x-axis is just the time in seconds. On the y-axis, you can sort of see the first thing we send out, the second thing we send out, and all the blue dots are essentially when we've sent stuff out. You notice that there's a bit of, you cannot just send everything immediately. There's a little bit of overhead even in AIO. However, in the lower chart, that's a situation when the Lambda function was just created, and we're going to send it traffic for the first time. In that case, you know, it's not used to getting 1,000 concurrent requests in one time, so it has to spin up a whole bunch of stuff. And this is all the magic that Amazon does for you. You can do some cheeky things, like you can measure the IP address, and you can also measure the thread ID and that kind of thing to try to reverse engineer the way that Amazon does it. It's hard. One thing you do notice, though, the moment that you've done this once, if you then send the second batch of lots of questions, then everything comes back in a more predictable pattern. So there is this notion of a cold state and a hot state in these functions, but you mainly only pay for it the first time you do this, which is fine. I'm willing to wait once. However, we did notice that, you know, it's great that I say I want to go at a sushi go, and then I send 1,000 requests from my laptop to the cloud. But I mean, there's going to be lots of network overhead, probably, which is not necessarily a great thing. What might be better instead is if we start some sort of SageMaker instance or an EC2 instance and just do the command line from there. And we're just curious in how big the overhead in this could be. And it's massive. The weird thing here is that basically we're waiting for the entire batch to come back. So essentially, you're waiting for the slowest thing to come back. And if you've got a lot of network overhead, it's actually quite sizable. You're waiting more than that you're actually computing something. And, you know, this would be the point in time where usually I would give you a live demo, but I'm not going to ask the kind engineer upstairs to do alt-tab and do all of those things. So here's basically what we get back when we run the command. I'm sorry it's static, but I can assure you it works. When you run this, you can see in AWS monitoring that you're querying thousands upon thousands of Lambda functions at the same time. The cool thing is we measure how long everything takes on Amazon side, and we can calculate how long everything takes on our side. So, this please. So this is the point in time where I started thinking, yes, let's really get kicking. We can really, you can call AWS, you can get more CPUs, and all that's great, so this will be great. However, there's a law in physics. There's this thing called Amdahl's law, and the idea is that if you have a program that 1% of the time cannot do anything in parallel because it has to sync, then actually the speed up, even if you have thousands of cores, is not going to be thousands. And I'll just take the naive number. This is the way it scales. If I have 1% of time that everything is syncing and I use about 60 cores, then effectively the speed up will only be 40. So what I did is I just looked at the output that I had before. I looked at all the time that stuff is happening on Amazon side, and I looked at all the time that I spend locally. I have my probability that I'm syncing, and when I make a chart of that, then even when I have 10,000 cores, effectively this suggests that I would only have 4,000. So this actually got me thinking. Maybe I shouldn't be too optimistic about the speed up. Because, you know, let's apply the math a bit further. And then I came to an even more shocking conclusion. Because if you think about it, if you think back of that chart that I just made, I am not waiting for everything to come back. I'm waiting for the slowest thing to come back. And the more things I send, the larger the waiting time is going to be. The slowest out of 10 is probably not as slow as the slowest out of 10,000. You could do a little bit of math there. You just sort of look for the quantile of the sort of longest tail end of a distribution. So, boring math formula, you take my word for it if you don't appreciate the maths. But now I said, okay, if I put those numbers in the same chart, it gets bad. We even get to a stage where adding more cores will actually make everything worse. Which is somewhat counterintuitive, because parallelism is supposed to be better. But it seems that there is some sort of optimum, that I shouldn't be sending too much traffic, because I'll be waiting for overhead more and more. So then you're wondering, how can I make this faster? And this is sort of an interesting problem. This is sort of the whole thing about scaling. This is an optimization algorithm, not even a machine learning algorithm. But I would like to find a way, preferably somewhat general, that I can maybe deal with this, because then I can finally stop using my laptop and I can live my life in the cloud. And if you think about it, this is the problem we had, and the whole point of where everything goes wrong is not the green part, but it's that red bit. Everything has to come back to some sort of central controller, some sort of central process, and that's where all the state gets handled, but it's also the bottleneck. That red part has to wait until all the thousands of green parts are done. And then you start thinking, well, if that's the way that you could look at it, then maybe the best performance boost you can think of is to stop looking at this in sort of batches, but to maybe start looking this in streams. How about I just have some sort of queue where all the simulations happen? And I first start with all of my members that I want to simulate. That's the yellow bit going into the blue bit. Then I still got my trusty old Lambda function that can sort of listen onto the queue, and it can start simulating. And then maybe instead of waiting for like the thousands of things to come back, I can also just say, whenever a new member comes back, is that member part of the 100 best things I've ever seen so far? If so, update the list of best things and generate a new character, put it in the simulation queue. And now, I can still do micro-batching. I mean, there's still some stuff I can optimize. But this is the reason why some of the people say that concurrency is not parallelism, but it may actually be better. Because I'm no longer doing things in huge batches, I think I will no longer have the Amdahl law issue that I had before. It'll at least be a whole lot better. And that's the part where I think the algorithm started hurting a bit. Yes? Yeah? Space? All right. It's a very interesting way of doing a talk. So, okay, in terms of the algorithm side, I've considered a bunch of things, and then stuff that I like about this flow. But Bas also had some discoveries on how to optimize this system as well.
So Chalice does a lot of work for you. It takes a lot of work out of your hands. It allowed us to go with a Lambda function and API gateway up and running within a few minutes. At one point, we started thinking, okay, maybe the call via the API gateway to Lambdas is a bit of overhead, and we just want to call the Lambda function straight away, directly, without this API gateway. It turned out to be a bit of a hacky way to get there. Yeah, our main issue with the API gateway was it has this limit for the maximum time of execution, which is 30 seconds. After this, your call would just time out. So if you make your simulations larger and larger and larger and larger, at one point it's going to cost you, it's going to take over 30 seconds, and then you'll start running into timeout problems. The maximum time for a Lambda function, however, is 5 minutes. So we wanted to be able to use that. So the problem is Lambda has no URL public to the internet. You cannot just call it straight away. You can, however, use Boto. So Boto is a library to call Amazon APIs. And then via Boto, you can call your Lambda function. However, it does not do asynchronous calls. So it's a bit of an issue when you want to run these kind of algorithms. There is this project on the internet, on GitHub, called AIO Botocore. It's kind of an asynchronous version of Boto, but it's a bit, not everything is supported. So there's a list of a few Amazon services which you can call asynchronous, but they're like sort of half tested, and there's warnings saying use at your own expense. And also, the nice thing about Chalice and this API gateway is you just have to use this app.route decorator. It will create an API gateway endpoint for you, and then route your calls to your Lambda function. If you're going to move away from the API gateway, you will have to do this routing logic yourself. So it's a lot of work to get this to work. Other point, how about cost? The cloud is basically you pay for what you use, and we wanted to know, even despite it was our boss's credit card, how much does this experiment cost? So Lambda pricing consists of two parts. One, you just pay for an invocation of your Lambda function. This costs $0.2 per 1 million requests. And second, you also pay for the time you use a Lambda function. You pay for blocks of 100 milliseconds. The price you see here is the cheapest price you can get for a Lambda. You can, with the Lambda, you have this switch. You can allocate more memory, and with that you get more CPU, but it will also make it more expensive. So with this formula, the price for making 1 million requests to Lambda cost $21. So let's say, extremely naive, you were to brute force your entire, all the possible combinations of your Sushi Go. Yeah, it's going to cost you a lot of money, and in that case, maybe just getting a big fat machine to do all the hard work might turn out cheaper. But we also discovered this algorithm converges very, very fast. You don't need to brute force all the 2 billion combinations. So with just a reasonable amount of simulations, yeah, it would end up costing about $10. And this would basically mean running 500,000 simulations. Well, yeah, then you're pretty confident about having the optimal order of cards. So this will cost you $10. And let's say you have a big fat machine with 64 CPUs, like somewhat equivalent to what you get with Lambdas. If you were going to run that for 24 hours in Amazon, yeah, it will cost you a little bit more, or approximately $76 dollars. There's this switch in the Lambda user interface. You can allocate more memory to it. With that, you also get more CPU power. So it's nice because, yeah, your simulation will go a little bit faster, and it's a very CPU-bound task that we're running. I think there's a next slide. Yeah. So if we were using the slowest possible Lambda, all our simulations would take about 20 seconds. But if we raise this if we raise this switch to the maximum, it turned out our Lambda ran 4 times faster. The number of seconds it would take will be somewhere between 3.5 and 5 seconds. So this is nice, but there's a trade-off. So you pay 10 times more in this example, and you get just 4 times speed up. We did find this optimum where our Lambdas would run twice as fast, so you pay half the price. So basically, you get to pay nothing extra, but you do get twice the speed up, which was a nice discovery. So you have to kind of trial and error with your Lambda functions to get the optimal between price and performance. Another thing, the default maximum for number of concurrent Lambda functions you can have is 1,000. You cannot raise this beyond 1,000, but if you're nice enough to Amazon and you're willing to explain you want to brute force a card game or run some simulation on a card game, yeah, maybe they'll raise the number of Lambdas for you. So some engineering conclusions. Lambdas, yeah, it's not really the use case for a Lambda, but it's nice that you can basically outsource your CPU power to the cloud. And yeah, combine this with async I/O, because basically with async I/O, it's if you have some I/O intensive task, yeah, that's a nice use case for running asynchronous. But yeah, if your CPU is going to run all the time and do some heavy crunching, it's typically not a good use case for running asynchronously, unless you can outsource it to, for example, Amazon. And then you can run concurrently 1,000 simulations and just wait until they get back. During our benchmarking, we did discover there's a big difference between hot and cold functions. So Lambdas, they have this hot and cold state. If you call a Lambda, it will spin up for you, if it hasn't done so before, from a cold state. And then, yeah, it remains in a hot state for a couple of minutes. So if you rerun your benchmarks, you're going to get different results, depending on the state of your Lambda functions. Just a generic concept in these genetic algorithms. State is a hard thing to handle. If you're going to run many simulations at the same time, you need some way to track your state, and if there's lots of processes running simultaneously, you might run into some bottlenecks in your algorithm. Also, program with async I/O. It can be quite nice for you. The basics are pretty easy to get right, but once you're going to get into a bit more programming with async I/O, it's kind of hard to get the details right. Sometimes there's this, you miss the async or await keyword in your code, and then you think like, hey, my code's running so slow, and it's kind of hard to debug these issues. There's also some scientific conclusions.
Yes. My girlfriend's watching this over the stream, and I suppose that you're all wondering, wow, you've spent so much time optimizing all of these things. We're doing like concurrent things and algorithms, and this is NP hard, and we've totally scaled everything out of this. So obviously, Vincent won. Nah. In fact, what the kind engineer, if you could move your mouse cursor to the middle of that screen and then click, you should see a play button. Yeah. So my girlfriend made me show you everyone that. Could you press it one more time just for good measure, please? Back to left arrow. Press it one more time, please. Right. So, good. My girlfriend, who's now watching, is happy. So, spacebar, next slide, please. Yes, so the truth is, I mean, we love doing this, but we ran both the batch thing and the more streaming thing. Like, we totally played around with lots of cores. Seeing the numbers go up was fun. But unfortunately, we did find out after implementing everything and optimizing a fair bit that the algorithm tends to converge after 2 iterations anyway. In this case, we did have a lot of fun. Like, we did learn more from the road than the destination, because I do think, like, really, that we've got a nice little pattern here. And if you want to do more grid kind of stuff, this is actually somewhat powerful, and the costs behind this are actually kind of interesting. So, the conclusion, the squid is the best card in Sushi Go. Note, though, that our approach is immensely naive. I mean, the game has a rock, paper, scissors element in it. You're totally not going to capture that with a list of cards that you put in a certain order. Nevertheless, again, our approach scales well and is fairly cheap. We might still have a bit of a problem with premature optimization. I think that's fair to mention. But once again, we really did have a lot of fun with this. We really did learn a lot about serverless. We actually gained a concurrency grid pattern, and we learned a lot about async. So if I can give you any advice before you leave today, spend some time with your colleagues, find this very silly problem, and optimize everything. I would also like to have a round of applause for the kind engineer who's been pressing all the buttons upstairs. And also to the ones that weren't here before. There was like someone who's giving a talk here and stuff was completely failing. Be sure you reach out to the previous speaker, because it was a bit of a bummer that a lot of these things failed. So reach out to her. We're open for any questions.
I think we've got time for a couple of questions. So if you can come down to the mic, or I can run up. I think this chap was. Do you have a question, or?
Well, we can also, if you scream the question, we can also just repeat it. That might be.
Hi, that was super entertaining. Thank you.
Thanks.
Just a quick question, actually. I really love the idea what you were saying about how you guys have a free Friday each month, kind of work on stuff, and I just want to hear a bit more about that.
I want to emphasize that we agree.
Yeah. I was going to say I'm going to try to make the pitch when I get back to work. So, do you mind just kind of expanding a bit more how it works? What kind of good things have come out of it? I mean, obviously this is a good one, but
Yeah, sure.
anything else?
All right, I'll take it. So we have once a month, we have, or every 4 weeks actually, we have this Friday where you do not work for any clients. So everybody goes to the office, and basically you're allowed to do whatever you want, as long as it's kind of work related. There's no mandatory requirements whatsoever. Just go and hack away. So sometimes people want to pick up a new programming language and they read a book. Sometimes people want to work on hack away on some project like this one. There's really no requirements whatsoever to do so. And sometimes fun things come out of it, and sometimes you're hacking away for a day and you think like, what have I done today? Nothing's working. Okay, that can also happen. But it's always fun to learn new things in these days.
And if I can recommend you anything, if you're going to make the pitch to your employer, if you look at what we've done, I mean, we've spent a fair amount of time on this, but here's some of the stuff we got out. We learned a new programming paradigm. We taught ourselves a bunch of new cloud tools, and we have a cool talk for a conference. So that's still a return on investment. And you allow yourself just that extra bit of creativity to work on things that you wouldn't otherwise do, which might actually save the day someday.
Okay, I think we've got time for one more question. I think this.
If my girlfriend ever wants to play another card game, I'm totally prepared this time.
Yeah. Okay, so quick question. Would you say that you failed because the modeling of the game was flawed? Like if you change the implementation of the game in Python, would it be better it would work?
That sure didn't help. But so again, one thing you have to keep in mind with this, you're not allowed to use the laptop while playing the card game, right? So that's a hard limit. So the only thing the algorithm can do is teach you some sort of heuristic, maybe something that you don't know. And again, you could go for the deep reinforcement learning thing, etc. But my girlfriend would no longer want to date me if that's how we spend our Sundays. But definitely, yeah, if you really want to do this properly, there's a bunch of stuff. And also, if you're going to do the algorithm streaming, by the way, the whole genetic portion of the algorithm changes a bit, right? You no longer have population, so there's some numerics you have to...
Okay, I think we're going to have to wind it up there. Thanks once again, Vincent and Baz.
Thank you.